ठीक है, लाइव है।
मैक कर दिया मैंने।
ठीक है,
पाँच मिनट में नहीं भेजता उसको, बैठे उसको निकाल लेते। ये वैसे बोल मतलब
क्या
कुछ बात तो तू लिख दे। Start with example 6.5.
ये तो तेरे को समझ आ गया था। अच्छा कुछ नहीं।
इवन तो रिकॉर्डिंग होगा तो लिंक नहीं का
ये तो म्यूट कर देना तो रिलीज करेगा।
कहाँ पे Hi, for those of you who have joined, can you hear the audio clearly? Just respond to me in the chat window if you can hear the audio clearly and if you can see the video clearly. I'll start the office in 5 minutes. I'll give some time for others to join, and then we'll start with the office hours today. I'll mostly be covering amortized algorithms and one or two doubts that were asked to me in the thread. And okay, good. So at least the audio and the video connection are good. We'll start in about 2 minutes. Let's see if anybody else wants to join. Douglas, can you do a full screen on your video? Is that making it better? So I think this is the maximum size that I could share with you. I'll try to see if I can increase the size of the document because the document is full screen on my computer. Let's see. Yeah, I think that's the maximum size I have, Douglas. So I think you try maybe increase like on try the YouTube video on full screen. Maybe that'll help you. Okay, so let's start today's office hours. So I had a few questions regarding. So we'll be considering amortized algorithms today, and we'll be covering amortized algorithms using the potential function, as we have seen in the video lectures. Uh, okay, let me try this. Is this better now? Okay. So the first question anybody have would have is like how to decide the potential function. So okay, so the potential, there is no fixed way to decide the potential function. It mostly depends on the type of data structure that we're using. And so today, to decide how to use a potential function, mostly I'll go through the practice problems that we have and then try to see if we can get some intuition about the potential function. So in the office hours, in the video lectures, we saw that for the arrays, we chose the length of the array as a potential function. And why that would work as a good potential function, because if you think of potential function in terms of potential energy, the energy should increase as the data structure size increases. So it's like the potential of the data structure increases as more elements are added to data structure. So in case of arrays or queues, you see that inherently these structures are linear. That's why considering a potential function that is linear would work with these cases. But if we see some other practice problems, there we have to work with heap trees, binary heap trees. There we know that uh, maybe we can't just choose like the number of elements in the tree as a potential function. Maybe we need to choose the height of the height of the tree as the potential function. So it mostly depends on the data structure that we have. We can have a primary intuition about it and then try to see if that works with an analysis. And if that doesn't work, then maybe we can choose another potential function. For an example, let's start. Okay. So like the first thing that I would do is that consider the complexity of the data structure. So like in case of the array accessing the function, most of the things are linear in nature. That's why I would go with a linear data structure. But in case of a tree, it's log n, you have to consider height of the tree. That's why I choose like a logarithmic potential function. So let's see for this problem 6.5, if we can, where we have to implement a queue with two stacks, what kind of potential function do we need? So like I mentioned, uh, with two stacks. So let's see how a queue works basically. For a queue, there are two basic operations. First one is add and second one is delete. So basically if we can mimic these two functions using two stacks, then we are basically done. So again, with q I get a intuition that there should be a linear potential function. So but before that, first let's just see how we can implement a queue with help of two stacks. So let's say we have two stacks, we keep two different stacks, stack a to add and stack d to delete from. So if this is our stack, initially both the stacks are empty, uh, and if we want to add an element, we would add it to stack A, add to stack A, and if you want to delete, delete from stack D. So okay, that might work. So in the base case, when there is no element, if we add an element, it will go to the first stack. If we add another element, it will go here. But now what if we want to delete? We say that we want to delete from stack D, but currently the stack is empty, and we know that when we delete, we need to give this element 1 as we should return this element 1, not 2. So naturally I would think that I would pop all the elements from A to D, and my A would become null, and then I could pop the first element from stack D and return it. So the delete operation, if D is empty, would just be to pop all the elements from A and push to D, and then pop the first element on top from D and return it. So that's how we return it. And if D was not empty, we could just pop the element on the top. So this is how I want my two stacks to work as a queue. So what could be the potential function? Before I go forward, I'll just check the chat if there are some questions. Uh, okay, so there are no questions. So I guess you can see it clearly and hear the audio as well. So let's see. Like I said, we should basically think of a linear function. So, and as we are using two stacks, can we just use the length of one of the stacks as a potential function? I have the intuition that because we are using two stacks, our potential function phi of d should be like the 2 times the length of uh, any of the stacks. So let's see the stack that we add elements to. So if I choose this as phi, I know that this is linear, and because I'm using two stack, I have the intuition that it should be twice the length of the stack A. Now with this potential function, let's see, like the cost of insert in a normal case would be C of insert would be is 1 normal case, and C of delete is also 1 in case of a queue. Now we want to find that the C cap of insert and C cap of delete for the two stack problem. Okay, so we know that C cap of I is given by C of I plus phi of di minus phi of d of I minus 1. So let's write that C of d subscript I is given by C cap of d subscript I plus phi of di minus phi of di minus 1. And we know what the phi of di is. It's just twice the length of A. So in that case, this equation becomes C cap of di is, we know that in normal case we need sorry, this is for insert. So in normal case we have 1 plus phi of di is twice the length of uh, a of I minus twice the length of a of uh, I minus 1. And we know that these lengths differ by just one element because we are adding one element and it becomes twice. So this would become 3. So 1 plus 2, that is 3. So basically we can do this operation in constant time. Are there any questions? Yeah. So this was the insert operation that I'm showing. So in insert, you just add elements to stack A. And when you want to delete an element, then there are two cases. So I'm going to consider those two cases. So this was just for the insert case. And why I chose 2 times the length of I, because I have 2 arrays. That's why I had the intuition that I should, you know, so that's why, like, you are using two stacks. Like in the video lecture, we saw that we are using one stack, so like the length of one stack. But in this case, we have to keep track of both. That's why I chose two. Like that was just my intuition. And if this works with my intuition, then it's fine. Then again, if this does not work, then while calculating it, I might find that okay, why this is not working, and then you can backtrack and see what was wrong with it. But for now, this has worked, so I'll stick to my potential function. So let's look at the delete operation. How it could be performed. And now the delete operation depends on B. So there can be two cases. Case 1, if B not empty ty, then what we have to do? Pop from B. So if B is not empty, what we have to do is just pop from B. And so our equation, this equation, and from this equation, if you see, our phi of any di is not dependent on B, and in this case mod of A remains the same. Hence, therefore, phi of di is equal to phi of di minus 1. And if you plug this into this equation here, you would just see that these two terms, phi of di minus phi of di minus 1, would just cancel out each other, and all we have to do is the value to the delete is just pop is just 1. That's why we return just 1. So this equation just becomes 1 because the value to pop from D is just 1. So that's why this operation again is constant time. But this is for the case when B was not empty. And then let's take case 2 where B is empty. Now what we do is that in case B is empty, we pop all the elements from A and keep on adding, pushing them to B. So like pop the top from A, push it to B. Pop the next element from A, push it to B. So what we are making is that we are making A to be empty and adding everything to B. And then once A is empty, we pop the top element from B, and that's the element that we want. So in that case, so there we are making uh, A of I times pop operations, and also we are making A of I times push operations. Just make it clear, pop operations from A, push operation to B, and final pop operation from B. So let's see how our function, so let's see in that case how would you write our equation. So in that case, our equation is, so the amortized cost would be 2 times the length of I plus 1. So just let me copy this. Wait, let's see if there are some doubts. Okay. Oh yes. I mean D. Yeah, this stack is called D. Sorry, I just lost it here. So the second stack is not B, it's called D. Okay. Okay. So our C of AI becomes, so the operation, because there are uh, 2 times A of I. Uh, Sorry, what's the? So initially there was I minus 1 elements in A, and then what we're doing? Huh. And this one for this final pop, and then our new phi d becomes 2 times a of I, which is in this case is 0, but let's, for the sake of the equation, let's write a of I. The length of a of I is 0 after this operation basically, and phi of d minus 1 was again 2 times a of I minus 1. So basically this becomes, this value becomes 0 because we are popping everything mm, from A. So what we are left with is just sorry, I think I wrote this. This is like this. So what we are left with is just 1. So again, we see that even in the case when B was empty, our time to delete from our 2 stack queue is still constant. And I think that's why we can conclude that in all the cases, both NQ and DQ, that is both add and delete, we can say that we can do both those operation in constant time. Okay, let's see the chat. Okay, I don't see any comments on the chat, so I'll move with the second question from the practice problems. Let's see which question to do. Okay, so 6 point, I think somebody asked for answer for 6.6. Let's see. I think before going to 6.6, let's choose a question which has a different potential function, a non-linear potential function. Okay, let's do 6.2. Okay, so in this case, they have given us a data structure. It's a binary min heap with n elements supporting the operations insert and extract min in big of log n worst case time. So give a potential function phi such that the amortized cost of insert and the amortized cost of extract min is constant and insert is big of log n. So again, now that they have mentioned the data structure, it's some binary main heap. Basically, it's a tree. And also they've mentioned that we are looking for a final worst case value which is big O of log n. This should give you some intuition that the potential function, if we choose something to be linear, it won't work. So like if you have any intuition for this, it should be that the potential function should be logarithmic. Okay, so but what could it exactly be? So we are thinking in terms of a tree, and if we are thinking in terms of a tree, we'll think in terms of the depth of the tree, and we know that we can get the depth of the tree based on the number of elements in the tree, in which is basically the log of the number of elements in current number of elements in the tree. So maybe that could serve as a good potential function. Let's see. So in that case, if given like the, for an element I, its depth is given by, let's say, okay, let's see, huh. Oh, and also I forgot to mention one thing, that it's a complete binary main tree.
The tree is always complete.
Yeah, so for an element I, its depth depth is equal to, let's call it d of I is equal to log to the base 2. So I won't be writing log to the base 2, but you can assume that it's log to the base 2, the number of the current number of I, and it's log of I only because this tree is complete. So just take that into consideration. That's a disclaimer that its depth is log of I only if the tree is complete, which in this case it is. Okay, so we have a notion for the depth of the tree, and how can we write the potential function? So let's see, in the length we just we knew that the potential function in case of arrays was like the length of the array, the total, so it depends on the total number of elements. So here also, if we can calculate the sum of all depth for all the elements of I, maybe that could serve as a good potential function. So maybe let's say phi of di state I could be like the summation of this di for I equal to 0 to n, the n number of if you have n number of elements in I. So let's see if this can work as a good potential function for now. And so, like, if you remember from the video lectures, we would ideally want a condition where phi of d0 is 0 and any phi of let's see, just of di is greater than equal to 0. This would allow us a very good analysis on the amount. So the total cost is then always in so if this is the condition, then we could find a good bound on the total cost of the operations. So are there any questions at this point? Okay, well, wait, I'll just look at the questions for a minute and try to answer them. Okay, so there is a question that it doesn't mention that binary trees are complete or not, but binary trees, by the way they are implemented, they are not stored as trees. Basically, if you know, heaps are stored as arrays, and if it's a binary tree, it's always complete. So if you see a binary tree, it's not stored as a tree. It would be stored as like if you have an array, it would be the length of that heap, and then it is zeroth element would be the root, and like if for every ith element there is the parent, and 2i and 2i plus 1 would be its children. So this is how you store a heap. So if you want to find the children of a root, then you children of the element I, you just do 2i and 2i plus 1. Similarly, if you want to find its parent, you just do the floor of I by 2. So that's how it is implemented, and that's why it's complete. Okay, any other question? Okay, and let's see, like, what are the initial cost, like the C of I, for insert and delete. We know that in case of heap trees, the initial log of ni if log of n if there are n number of elements, or ni if there are current state I there are n elements. And similarly, even for delete, it's like just do insert cost C. This is not C cap, this is C. And then again we would try to write our potential function. So should always start with this equation. If we know the cost small c of di, then the way we have defined the potential function, c cap of okay, I think this is this way. That's what I was confused about. Yeah, it is this way. C cap of di is ci plus phi of di minus r. Now this is correct. I think even if I wrote this incorrectly above, just please make a note that c cap of di is given as c of dy plus delta phi. And now we know that this is log of ni plus summation of log of di, basically your di I going from, the I going from 1 to n minus summation. So in this case, I goes from, I don't know if this is the best way to write this, but I goes from 1 to n minus summation of, it's the same thing, log of di, but in this case, d minus o. Okay, okay. It will go from, yeah, to n minus 1. And we can write this summation as summation of log going from n plus log of ni. So what I did is that I took out log of ni from this first summation. So this summation becomes this summation, and these two can then easily cancel out. So what we're left with is log of n, and okay, and there is like, that is finding the last element and inserting it, so plus 1, so it can be any constant. So in this case, what we are left is this is again big O of log of ni, n basically, because there are, actually we can drop this I from n, because I think, yeah. So is there any doubts about it? I think I crossed out a lot of equations here. If there is anything that you don't understand, please mention in the chat. So now you can see that our intuition for the potential function to be logarithmic has worked in case of insert. It is giving us the bound that we wanted. But if this would have been linear, I'm sure that in this case here, instead of log of ni plus 1, it would have been linear. This function would have been linear, and then some linear per logarithmic, it would have given us a linear bound. That's why our intuition of choosing a potential function that was logarithmic has, like, that was the correct intuition. And that's basically, I would tell you that if you try enough problems that take into consideration both like data structures like stacks and queues and also trees, then maybe you'll develop this intuition of picking out the right potential function. And even if you pick the wrong potential function while doing this analysis, in this step where you calculate the c cap of di, you will find that your potential function was wrong, and then you can back iterate and choose the right potential function. Okay, so let's see now an analysis to extract min. So what extract min is just that extracts the minimum element from the array, and so when we remove the element from the array, the length of the tree increases. I'm saying it array because heap tree is saved as array, so it's just the tree. If you're removing an element from the tree, the length decreases. So in this case, let's see how this equation changes. So I think I should have saved the previous equation. That's okay. Again, this operation takes us log of n time. Wait, let me see if there are some questions in the chat. Okay, no questions in the chat. Log n plus, now you see in the ith state the element has our tree has n minus 1 elements. In the previous case we added the element, now we're deleting it, so now we have n minus 1 elements, and in the I minus 1 state we had n elements. So this summation of log of di would go from, in this case it would go from 0 to n minus 1, but in the previous state the potential function would go from n. This is exactly the delete step, and again we can do the same kind of analysis. We can do this n minus 1, and then we can subtract, oh sorry, this is minus, and then we can subtract. So basically we can write this as this plus log n. So we could have written the second summation as this. So if we open the brackets, this becomes negative, and most of the things cancel out nicely, and we are just left, again we are left with a constant. No, in this case we are left with a constant, so we can just say that the extract min operation is constant time from this analysis here. So you see, I just manipulated like the summation and got to this answer. So that I think that answers both the questions in the problem. Okay. Now, are there any doubts? So I won't solve like in detail the next problem, but let's just try to see if we can find the potential functions for the remaining problems, and then maybe you could do the analysis for the remaining parts. Does that sound good to everyone? Okay. So I didn't do 6.1. So let's see if we can. Okay. I think somebody requested to for 6.6. Okay. So then let's just try to find the potential function for 6.6, and maybe like I think they have given an answer in the instructor solution for this. So maybe you can refer to that. Oh no, okay. But at least let's try to find the potential function. So I don't want to exceed the time limit that we have, and still I want to do a couple of more problems for dynamic programming as well. So oops. Oh, okay. What happened? Design. Okay, so you have designed a data structure to support the following two operations. Okay, so insert into X. It's a multi-set, so it can have duplicates. Insert into X, delete a larger half from X, so delete the larger n by 2 elements from S, where n is the number of elements S. Explain how to implement data structure so that any sequence of M insert and delete half operations runs in O of M time. Your implementation should also include a way to output the elements S of n in O of n time. So if you can see, this problem has a hint within itself when it says that you should be able to print this all the elements in your data structure in linear time. It means that you should choose a data structure that is similar to arrays. Like even in arrays, if you want to print all the elements, it's in linear time. So this could probably give an intuition on what to choose as your data structure. If you use a tree or something like, not just okay, there could be many options, but I think because this statement says that you should print, I think that we can try a linear data structure. Like we can just try arrays in this case. So if we kind of choose S as an array, so how does array insert work in array? We usually insert at the last. So it's like if we have an array, so let's just say that we not overflow the array, the length of the array, we have enough space for all cover all the elements, and we have a pointer that points to the last element of the array, and we insert at the last. And then for the delete larger half operations, we need to find the larger half. So basically that tells me that if we somehow are able to find the median of this array, then all the elements to the right of the median are larger, the would form the larger part of the set, so the larger half of this array, and then we can just delete them and just copy the remaining elements, and that will become your new A. So with an array we can perform these two operations, but then how what to choose as the potential function? Yeah. Okay, so are there any questions till this point, why we are going with a linear data structure? Okay, so okay, so with arrays we have previously chosen just the length of the array as a potential function. So from the previous cases you would think that you can just choose this as the if A is the array, if A is the array, our data structure, then phi of di is mod of A, and we could start with this assumption, go ahead, but then we would soon find out that our operations in our operations we have to insert operation is pretty straightforward, we just insert the end, so it's a constant time operation. But with the deleting the larger half, we need to find the median, and there are various algorithms to find the median, but I think if we use something like a quick select algorithm where we just randomly pick a pivot, so it's very similar to quick sort, but instead of sorting the two remaining parts, so we pick a pivot, we partition the array into two lists basically, one less than the pivot, other greater than the pivot, and then we do quick sort on the remaining two lists. But in quick select we just pick up the we'll just see that if the current pivot falls at the n by 2th index, then we have our we have our median. Otherwise we go to the uh, array which is greater than n by 2, obviously, because there we would have our median. So this is recursively you can do these calls and find the median. So inherently this should take linear time. So I think students have mentioned some links in the Piazza post to this, how to find the median in linear time. But anyway, that's not the question that's asked in this problem. So let's just say for now we can say that we can find the median in linear time, but then our potential function is basically dependent on another function to find the median. So that's why we just can't choose uh, just the length of the array as our potential functions. We need to have a constant as well here. And you see from the analysis why they are giving 2 also here is because I think like the intuition beyond that was because we are going to delete in the end this larger half of the elements, we'll be left with half of this. So the half of this would then be like k times a. So otherwise we have to deal with fractions. So when we do the delete operation, our aim, the new state that we have would just be like k of a. But if we choose this as k of a, then this becomes just half. So that's why I guess not to deal with fractions, we are choosing this to be 2 times k of a, so that this operation just remains k of a. And that was the intuition behind choosing this as the potential function. And I think the analysis is covered pretty well in the post. So like I'll ask you whether you want me to cover the analysis, or we can go forward with some other problems. Okay, so let's just move ahead. So somebody asked me, let me look at the office hours, if there was any other question that was asked. Okay, 6.6 is done. uh, then let's just try to, do you want to solve a dynamic programming problem now, or okay, let's just solve the practice exam problem 2.1, the dynamic programming problem. I think if you now with this idea of potential functions, and I think with the feedback that you have from the TAs, I think exercise problem set 6 should be covered. And if you still have any doubts, please post on Piazza and we'll definitely get back to you today itself. But I think that let's move to practice exam problem 2.1. Okay. Okay, let's go to a different page. 2.1. Oops. Okay, so I know the solution for this problem has also been provided, but let's just see that what would we be expecting in exam, like how detailed the analysis should be, because I guess in the first exam most of you might have lost points because either you haven't provided correct inductive argument, or if you did the asymptotic analysis just by mentioning that there were two loops. So what kind of analysis are we expecting while checking the problem? So maybe that will help you, how detailed your answer should be, because I think you by now you might know the approach for this problem. So let's just see that you have been given a tree with n leaves. So the leaves are fixed and they have certain weights, and then there is a cost function here which basically, okay, okay, so the cost function depends upon the weight of the tree, the weight of the leaf, and also the depth of the leaf. So the depth of the leaf from the root. So okay, and number of, okay, no, sorry, the di is the number of edges, so not the depth, the number of edges from the root. And oh yeah, and basically the depth would itself be the, yeah. So scratch it out. It depends on the depth of the tree and the weight of the leaves. So we need to provide dynamic approach to find the minimum cost. So you know, with dynamic programming, while I was taking this course, there are like two ways. It's first try to find a prefix solution. uh, like if your problem is like, if you're a of I, so can you guess a of I from a of I minus 1, or would you require uh like a, so a of ij and then iterate between I and j. So these are the basic two ways, you can solve dynamic programming problems, or most of the problems that are in the book. So in this case, you somehow get the intuition that you always, so if you see, this problem is very similar to the Hoffman encoding problem, like if you have optimal, or the optimal binary search tree problem, where you have a, mm, you have a, first initially you have like each node as it is, and then you combine any of these two to form a tree based on some criteria. So let's just say that, combine these two maybe to form one root, so this would become like three, you know and then this is here. So then you combine these two to become another tree. So there is one tree coming from the left, one coming from the right, and that somehow gives me an intuition that there are two trees I and j, and then I have to find this the best split k between them, such that the left tree and the right tree, based on the cost function that we have, we would get the optimal solution. This kind of approach, like the prefix kind of approach which we use, find the, let's say, the maximum subsequence or something like that, that won't work here, because inherently this problem, it's like combining two parts to form one part, and then this gives me an intuition that there should be three variables in our recurrence relation. So at this point, is there any question? Okay. And also we want like the bottom up approach, so we cannot do memonization. So there were some questions about like what is bottom up approach like. So whenever I am doing finding the, for the ith step, whenever I'm finding the value of the ith step, I use the previous steps, and the basic intuition that I minus 1, I minus 1 and similar. So basic intuition that when I calculate the ith step, I should have the values. I assume that I know the answers for I minus 1 and the previous values. So this is like the bottom up approach. You can save these values. So it doesn't mean that bottom approach you can't use a table. You can use a table to save these values, but when you calculate the ith step, you already know what was in the I minus 1 step, and you don't do any calculation. You just probably make a decision which of the lesser values you choose. So that's the bottom up approach. So there were some questions regarding that as well. So how would you solve this problem using a bottom up approach? So let's just say that currently we had this tree as our pf ij. So how could this tree have been built? There must have been a split k, such that you know such that this there was a left tree, there was a right tree, which was combined to form this tree. So let's see if this tree was split at some value k. So this would have been the left tree in that case, and then there would have been a right tree as well. uh, Sorry, right tree would go from k plus 1 to I, and there would be some cost involved as well, some constant c, because you are combining two trees. And how do you find this cost? Basically, if you look at the problem, uh, when we combine two trees, our depth increases by 1. So this gives me an intuition to calculate the cost of the tree, and because our depth is increasing and we know how the cost is calculated, it's just summation of the weight of the ith node plus di, and you can just use this to calculate the cost of the tree, between I and j. So from I going from, so let's just call this x, and x goes from I to j. So this gives me some intuition about the recurrence relation. So exactly the recurrence relation would look something like this. Uh, so so initially, if the base case, let's look at the base case. Base case when I is equal to j, it's 0, so it's just the one node, so there is no point in combining them, it's still one node. But when I is not equal to j, then we can write p of ij as p of
k plus 1 to
uh,
j
p of ik plus p of k plus 1 to j plus this cost that we calculated. I'll just copy over this, and we have to minimize this cost basically. So this would be a minimum over k,
first line of the
k going from
recurrence.
I to j. So because we need to find the optimal solution, we need the best split, and the best way to find it is check for all k's between I and j is not inclusive here. So basically this is like this. The best way is to find this k, iterate for this k, and because this is a constant, we can pull it out of this minimum and just have it in the end here. So does that make sense? Okay, I think that makes sense. Okay, for this problem, if you see, it just says that define an appropriate recurrence for the subproblems. But in another problem, I guess in one of the practice solutions, 4.1b or something, there they said that give an inductive argument as well. So I would ask you to please very carefully look at the problem statement. It just says that define an appropriate recurrence relationship. So we have defined an appropriate relationship, but we haven't given any proof of correctness. But it didn't ask for one. But if it did ask for one, then I would tell you to write some kind of or provide some kind of inductive argument which shows that this is like this would give you the optimal solution, or provide some inductive argument. So but in this case it just says that define recurrence solution. So that's one thing that we look for while problem solving, checking your papers, that if you have covered all the aspects of the question. So just make sure that you look at the question while going ahead, that do you need a proof of correctness as well. If not, then you can just proceed ahead. And now it says that implement an algorithm. So basically, if you have the recurrence relationship, implementing the algorithm is not that difficult. But again, while implementing the algorithm, you have to take care of the base cases. First, to define your structure, like the table. In this case, it's a matrix of, I guess, n by n. Mm. So, so because n by n, so these kind of problems which usually involve three variables, it creates a matrix of n by n. And what we try to do is that fill this top of the matrix. Like if we look at the how to write the code, usually for these kind of problems, if this is the matrix basically, uh, you're trying to fill this top half of this matrix, you know and your most optimal solution. Yeah. So I don't know if this figure is clear enough, but let's see. So this is like the top triangle of this matrix. This would be the other triangle, but I'm not drawing it. So whatever element, so this I would go from here, I is this, and j would go from here to here. So well, I is less than j, so you fill this along the diagonal. So you in your base case, when I is equal to j, when I is equal to j, you kind of fill this diagonal. You fill this diagonal by ones, because if I is equal to j, you know that p of ij is 1. So you kind of fill this with 1. So even in your in your pseudocode, first you handle the base case where you know mm, your p of ij is 1. So for I in range n, p of I is 1. So this handles the base case. Now you write your recurrence relation. So it's basically you need 3 loops. So your I would go from 1 to n, whatever the, sorry, oh sorry, not 1, 0. I think I made a mistake here. It's not 1, it's 0 because there is no cost involved for I in range, you know, uh, 1 to n, and no, sorry. So your j, okay, your j goes ahead because that's the front of the range, and I goes from 0 to, so this goes from 1 to n, and basically your I is behind. So always, because you want to build this matrix, the top of the matrix, your I would always lag behind j. So your uh, I in, it's a standard template for these kind of problems, this the matrix multiplication. And so I would see if you see that you understand why it is in such a way, why it should lag. I lags behind j, and then your your k can go. So you here in this step, now you define your recurrence relationship. So basically you now you try to find the best split here. Wait, till now, are there any questions till this point? No. So now you try to find the best k for k in range I to j. You find this value. uh, you first define some min val as, just these are just the implementation details, and then for each k calculate this p of I, p of ik plus p of k plus 1 j plus the cost. So define a function to do that summation, which involves w and I and j and your d. So basically use this function to calculate the cost. This would be outside. So basically you can add this, basically you can, for now you could okay, calculate this, store it in some temp value, and then you can check if this temp is greater than min val, sorry, temp is less than min val. Then you could set p of, then outside, sorry, min val is temp. So this is just like the implementation, and when you once you come out of this loop, you assign p of p of ij that value, the minimum value, because you are iterating to all the case, you are bound to find one value that is the minimum, and just give it as the min val. And so this is how you could build it. So this cost actually you can remove from here because this is not part of the summation, and you can add it here as well in the end. So that just would save you some time, so that this function call you'll have to just make it once instead of I minus j times, j minus I times. So I guess something like this would work. And then now because you're building your matrix like along the diagonal, what would you return? What would this function return? So you essentially have to return p of 0 comma n. That is the value, that is like this top box, like the rightmost corner of the matrix. That means that you have exhausted to all I and j. That is like you have built the full tree, and then by building it, this is like the final cost that you have incurred, and that's why you'll return this. So this template kind of is similar for matrix multiplication as well, the best binary search tree, optimal binary search tree, and even for this problem. So I would say that for bottom approach, you can probably refer to this algorithm, or I think professor also provided his solution in the instructor's solution, so you can look over that as well. That is the intuition. So we have an algorithm and analyze the worst case performance of this algorithm. So again here I would probably advise you to look at how Professor Privy has given the asymptotic analysis. You just don't say that 3 loops and hence we can say that big O of n cube. Just try if you can find some relation. Just this is not don't just provide this one argument, and because this part contains one or two points, so try to give an recurrence, or some try to come for that solution rather than just mentioning that because there are three loops you get big O of n cube. Try to give some kind of mathematical proof, so and that will give you full points for all the cases, and then that's it basically. So are there any questions? Okay, so there are no questions, so I guess I have covered the doubts that were asked in the thread. uh, Just the solutions are provided for remaining exam problems, so I guess amortized, you can, if you haven't done it. Do we need to Okay, do we need to create a table with what the pseudocode produces? So yes, so this I have initialized this p table. So initially it was because I am using, in this case, and if you see, the temp is calculated using p of ik and p of k plus 1 comma j. So these values would already be in the p matrix, so otherwise you would have to calculate for them. And before I calculate p of ij, I have already calculated the values for p of ik and p of k plus 1 j. So this is just a constant step operation, they are already in the table, so I do need to have this p table. This is still the bottom of approach. It's just that while calculating the ij step, I have this intermediate, the value of the intermediate problems is already there with me in this matrix. So yes, I built that table. Yes, I have covered the potential functions. So there is no foolproof, way to come up with the potential functions. But for the exam, I would say you that there are like a few types of problems that you could have. Either it is to do with arrays or queues, or it has to do with trees. And for both these problems, you can get the intuition of the potential functions. So I would say that some data structure like arrays or something, you go always stick with some kind of a linear potential function, or there would be some hint if it's not like a straightforward potential function, like in that problem where it said that you should be able to print the your elements in n time, so you would get some hint from this question as well. But the main thing is that the more problems you solve, or the more type of problems you solve, you would kind of build the intuition for the potential functions. And even if you not just assume a potential function, try to do the analysis and see if are you able to get the correct amortized analysis from your potential function. If not, then while analyzing you will find that okay, this is where I went wrong and maybe this is how I should change it. So I don't know, apart from that there is a way to come up with a potential function, and that's it. So any other questions? Okay, so any questions regarding the sixth the amortized algorithm problem set? Mm, problem set 6, are there any questions? So yes, for 6.1, I guess the potential functions is not at all intuitive, but I'm looking at the solution provided, and it is kind of mimicking the dynamic arrays, and I think that was covered in both CLRS. So it is in the Corman book. I think dynamic arrays are covered. So if you kind of had read that before, from that you'll understand that this data structure, even though we are not mentioning what data structure this is, but it is kind of mimicking the you know dynamic arrays. So from that again you can get the potential function. So as I'm saying, there are only a finite type of data structures on which you can perform this kind of analysis. And if you have read through the Corman chapters and the video on YouTube, then I think you should be pretty good. And if you have solved all the problems from the problem set, I think that should be enough for this exam, I think so. So like they've done this table where they have calculated the I and cost per I, and from that they're getting like for each even power of 2 we have to reset it. So from that, they have kind of deduced the potential functions. Yes, even though it is not that intuitive, uh, I would say that if you had any previous knowledge of the dynamic arrays, you probably would have guessed this potential function. For 6.2, okay, I think we covered 6.2. 6.3, what is the total cost? N stack. Okay, so 6.3 problem is, I think it's just a variation. If what would you do in the base case where the base case is not zero, when uh, phi of d0 is not zero. So in that case, I think the video lecture pretty much covers it. So in that case, you just have to do some rearranging. You write ci in terms of c cap, and then try to get a bound on ci. So if you're if there is some, if in these kind of problems, again, if your phi of d0 is not 0 and this condition is essentially not necessarily true, di is phi of d0. If this is not true, what you can do is you can still use your potential analysis when assuming that this was true, the amortized analysis that you did, you can still use that analysis to come up with a bound for c of I, the total cost of operations. In that case, all you have to do is some rearranging. So initially this was like c cap of I is c of I plus this delta phi, basically. So what you can do is you can do some rearranging. You can get this on the other side, and then this rearrangement would help you find a bound, and this delta phi then becomes, this also gets on the other side, so this becomes minus phi of d of n and plus phi of d of 0. So that's a general strategy, and if you apply this strategy for 6.3, where initially there were S0 objects to begin with, you come up with the necessary solution. So you can still use your analysis for this case to come up when these two conditions are not met. So you can still do your analysis. So that's 6.3. What else? 6.4, I think. Okay, 6.4 is similar. I have just posted the solution for that on Piazza. You can check it out. I'm doing the similar operation that I did now, just rearranging the terms and coming up with an upper bound. And 6.5 and 6.6 we just covered. So I think that covers the sixth exercise for amortized algorithm, and also we did one problem on dynamic programming. So if there are any more doubts, you can just tell me now, or we can conclude this office hours. Okay, thank you all for joining. I'll clean the video and post it. If you want this Word document, I can also post that, but I think it's pretty much covered in the Piazza post, so I think it's better formatted. So maybe you should take a look at that, but I can still share this with you, and I'll try to put up the office hours video as soon as possible. Thank you all for joining. Have a good day.